Alright, so I had some tech issues / got interrupted / that's why the video stopped randomly, but we're going to pick up right here. So we're going to find the length of DC. That's the punchline of this problem. And it's saying, well, people, guess what? This is a tangent line. Thus, it's perpendicular to that. They're perpendicular to each other, tangent lines. So what we're going to do is invoke the Pythagorean theorem. All right. So what we're going to do first is find this entire length right here. That's A, that's B. We'll call that C. So a squared plus b squared equals c squared. Let's just find this entire length and then talk about other things. 5 squared plus 8 squared equals c squared. 25 plus 64 equals c squared. 89 equals c squared. All right, so on and so forth. You take the square root of both sides. I'm going to write it like this. C equals the square root of 89. Let's just keep it like that for a second. All right, so the whole thing's 89. How do we find this? All right, how do we find that right there? All right, well, watch this, people. AD and AB, they're both radiuses. Thus, since they're both radiuses, that's 5 as well. So, referring back to stuff we did all the way back in Unit 1, segment addition postulate. AD plus DC equals the whole thing AC. So we have 5 plus DC equals the square root of 89. Just subtract 5 from both sides. And DC equals, and it has to look like this when you plug it into a calculator. You have to close parentheses and then subtract 5. If you don't, your calculator is not very smart. It will mess up the calculation, but it's going to be about 4.43. All right, so that's how you do that problem right here. There's a good old Pythagorean theorem problem. All right. So same thing in number 2. We're going to use the Pythagorean theorem to determine if the triangle is a right triangle. All right. So remember, if this is a right triangle, this is a point of tangency, and that's a radius. All right. So basically, if this is a right triangle, it's saying BC is a tangent line. If it's not a right triangle, then it's not a tangent line. So it doesn't matter, that can be A, that can be B. C has to be the hypotenuse, don't you forget that. So A squared plus B squared equals C squared. We're going to get 10 squared plus 8 squared, parentheses 4 radical 10 squared. All right, it's probably a good habit to put this in parentheses. All right, so we're going to get 100 plus 64. So we're going to get 164 on this left-hand side. On this right-hand side, it's going to be 4 squared, radical 10 squared. All right, 4 squared is 16. Radical 10 squared is just 10. All right, they undo each other. So we have 164 equals 116. All right. So, not a right triangle. BC not tangent to circle A. All right. Let's make that a little bit smaller. Then over here, we got to find the length of AB. All right. Finding the length of AB. Well, how do we do that? All right. Well, we have some known information. We know in this circle A, we have a radius of 25. That's a radius of 20. All right, these are radiuses perpendicular to this right here. This is a common tangent line. So all I'm going to do is take this tangent and boom, bump it down there, 55. All right, then this is 20 minus 5. I'm going to take 20, subtract 5, so it's just 5. And now, I just got to find this length. I'll call that C, and we'll use Pythagorean theorem again. So Pythagorean theorem, incredibly important. Got all kinds of different places we can use it. $55 squared was that big number, plus 25 to both sides. C squared is going to equal 3,050. And it's going to be approximately, this one we want an approximate answer about 55.2. Okay, cool beans. All right. Now over here, we're looking at our iBook again, so let's make the iBook a little bit bigger. All right. Circles can share a common tangent line. All right, they can be internal or external. All right, so we're just going to do some super fast stuff. That would be a common internal, because see how it touches on the inside, and then we have a common external. Touches on the outside. Do it like that, good. All right. So common internal, common external tangent lines. Remember, they only touch at one point, so they're touching one point in two different circles. All right. So one circle can have two tangent lines from the same external point. So then we can also have this, all right? And the maximum is actually only 2. So if we have one random point here, we'll call this C. This is a tangent line. It goes just to D. It only touches the circle at one point. It went on forever. It still only touch. And then B. All right, and this was circle A. All right. So what is the relationship with DC and CB? Well, to keep it simple, let's just look at the theorem right here. If two tangent segments are from a common external point to the same circle, then they are congruent. All right, so that's a big punchline. Now we have tangent lines are perpendicular to the radius. Now we have if two tangent lines come from the same external point, then they are congruent. All right, now we're going to apply this to a couple problems, and then we're almost done. All right.